Okay, let's get started. So if you have a quiz 16, please turn it in. I have your quiz 15 and some 14s left. Are there any questions since last time? So if you haven't seen the announcement that I posted today, there's no take-home quiz on Wednesday. There is one today, but not one on Wednesday. And the homework will not be posted, the next homework will not be posted until after spring break. So you'll have a nice spring break and not have to think about this class. Although you should always be thinking about this class, but anyway. And I'm not biased in any way. Okay. Any questions since last time? So what did we do last time? What did we show? Yeah. So we did some pumping, and we came up with this lemma for CFLs. You ever wonder why it's called lemma?
Well, no, I do.
Okay, but because I asked it, right? So lemma is another term for little result or theorem or something. So it's a way of assisting a proof of an actual result. So if I wanted to prove that 0 to the n, 1 to the n, 2 to the n is not context-free, then I use this little, quote-unquote, little result to help me prove that theorem. So that's the reason why it's called lemma. Okay, well, what did we use this lemma to achieve? What were we able to prove? Yeah.
That certain languages aren't context-free.
Right, and one example of a language that's not context-free is?
0 to the I, 1 to the J, 2 to the K.
Yeah, so that's one that we did, or at least we started. I don't think we finished that one, right?
Yeah.
Yeah, so I think we did something like this. But what was the one we were able to actually finish? Yeah. So our familiar language, 0 to the m, 1 to the m, 2 to the m. Okay? So what was something that we delved into pretty deeply with regular languages and was actually the basis of why we made NFAs in the first place? So why did we make NFAs in the first place? What problem were they trying to solve? Yeah, but why did we even come up with non-determinism? Just to torture ourselves? Or was there a real reason?
Wasn't it to make it easier to work with them?
Easy to work with, yeah, that's a valid reason. But there was a specific problem that we solved with NFAs. And that was the problem of concatenation and star of two languages, right? So we did union with the product construction and all that jazz. But we didn't see an easy way to do concatenation or star easily with a DFA. So that's the reason we made NFAs. Well, what other operations did we show were closed with the regular languages? So we have union, concatenation, and star. What else did we get? Well, inverse, what do you mean by that? Because there are different definitions of inverse. Oh, complement, yeah. Yeah, so we had complement. And what was the other one? Well, if we have union and complement, what do we have? Intersection. So the ones that, so the closure results we have for regular languages, we have union, concatenation, and star. Those are the big three. as well as I can't spell intersection, and complement. Oh, by the way, so to show me that you're actually paying attention in class, I know you all are, but to actually show it to me, don't spell complement with an I. I've had people do that before, so make sure it's spelled with 2 E's. Okay, so we have a list of operations that regular languages are closed under. I think we did majority at one point, and so there are other operations we can do too, but these are the main 5. What about context-free? So which of these 5 are are context-free languages closed under? Or at least we have shown so far to be closed under. I think we did this in a lab.
I think we did concatenation star intersection.
2 of those are right.
Concatenation star.
Yes. And what was the other one? So the U and ends with union. Union, right. So let's actually briefly go over why those are the case. So why are CFLs closed under union? Yeah. Right, yeah, so you OR them, right. So the new start variable goes to the first one or the second start variable of the 2 grammars that you have. And I claim that we get concat as well as star. How did concatenation work? Yeah.
Just go from S to, and you have 2 variables.
Yeah, S1 then concatenated with S2. Yep. And then how did star work? So this one was a little more complicated. Well, what is in the star of every language? Empty string, right. So we have S going to empty. But what else could S go to in this case? Yeah, so there will be another S, but what else? Well, think about how star works. Think of the NFA that we did for star. So we can go through the machine, and if we wanted to, we can come back and go through the machine again if we wanted to. So how would that work here?
Was it like S1 S?
Yes, good. Because we could reach into the grammar and get a string out of it. And if we choose to, we can go back through the new grammar if we wanted to. So we can go in and then come back around if we wanted to. Cool. So any questions about those 3, though? So this should be review. So then you may be thinking, okay, well, there are 5 things on the left list and 3 things on the right list. So are these 2 lists the same? Are context-free languages closed under intersection and complement? So that's something you may want to know. So I'm going to put this as a question mark because we haven't answered that here. So what do you think? So you may think, well, go ahead.
Couldn't you just do the intersection of 2 context-free languages that recognize none of the same strings at all, and then you have the empty and that would be regular now?
Right. So remember what closure means. It says you take any 2 context-free languages, the result is context-free. For those 2 examples, yes, it is. But is it true in general? Yeah. So if we have a counterexample, then it'll show that it's not true.
So is it not true?
Well, that's what we're going to figure out. So what do you think? So let's think about it. So remember the question where I had, where we took a context-free language and intersected it with a regular language. What was the result of that? It was a homework question. It was always context-free. So the reasoning behind that was we could do two operations at the same time. Take a transition of the DFA and apply a set of rules with a variable at the same time. We'll think about it in terms of a PDA instead. Well, could I take a PDA here, a DFA here, and intersect them in a reasonable way? And it actually turns out to be really simple to do. What you do is, in the resulting PDA, the stack operations are what the original PDA would have done because the DFA does not have a stack. So if we take matching transitions, and by matching means reading the same things, then when I do the intersection, well, the stack operation there is what the original PDA would have done. Here's the major technical challenge here with intersection. If I take two PDAs and I try to intersect them, now I have two transitions that modify the stack. Which one do I do? Right? So therefore, they're not closed in an intersection, right? Because this one method doesn't work, it therefore is true that they're not closed. No. Okay? So that's just something that you just got to be cognizant of. Okay, so intersection seems hard, but if we can get complement, so if we can show that they are closed under complement, can we get intersection immediately? Yeah, because if I have union, which we definitely have, and supposing I have complement, then I can get intersection out of it because it's just De Morgan's law. So let's see. Do we think they're closed under complement? Well, how did we show that they were closed under complement for regular languages? How did we show it that then?
We took every state and flipped if it was a final or not final state.
Yeah, we flipped which ones were final and not. Right, good. Could that same idea work for NFAs? Not DFAs, NFAs. If I just flip the states final and non-final. No, in fact, we've seen an example where that doesn't. Are PDAs deterministic or non-deterministic? Non-deterministic. So therefore it doesn't work because this one idea didn't work, right? Again, no. You see this type of argument all the time. I've tried 10 ways and none of them work, so therefore it doesn't work. Okay. So, but if we do provide a counterexample, then it clearly will be not closed. So let's prove that they're not. So the result I want to prove is CFLs not closed under complement. And independently we can do intersection, but yeah. And so one thing you should notice here is we're going to prove this, obviously. That does not imply immediately that they're not closed under intersection. It could very well be that they're closed under union and intersection, but not complement. And in fact, we will see a set of languages that has that property. We'll also see a set of languages, maybe on Wednesday, where they're closed under complement, but not union or intersection. So it's pretty weird. So yeah, so just from this, don't immediately conclude that they're not closed under intersection because it very well could be. But they're not in this case. So not closed under complement. So how would I prove this? How about I prove that they're not closed under complement? Well, what does closed under complement mean? It says take any CFL, complement it, and the result is a CFL. What do I have to do to prove this? If they're not closed, all I need to do is find one example of a CFL whose complement is not a CFL. Yeah.
And by not a CFL, do you mean like do you mean a regular language or something broader than a CFL?
More than a CFL.
Oh, okay.
So something like we would prove with the
language is also context.
right, every
So
regular
that
language.
that would still be closed as well.
Well, we already know regular languages are closed under complement. Yeah.
No, but if you ended up, like, say your complement was a regular, that still is closure.
Right, yeah, yeah. That would
So you
still
have
be.
a broader language.
We need something of so another way you can think of it is so if we think of regular languages as inside here and CFL is here, what I want is some language in here such that when I apply complement to it, it goes outside of the CFL bubble.
So just take the complement of the context-free language, or the one we just proved is not context-free.
Only one complement, but yeah.
Yeah.
Yeah. So what is a worthy candidate? So let's try, it may not work, let's just try looking at the complement of 0 to the n, 1 to the n, 2 to the n. And then bar that whole thing.
But if you double bar it, then you just get that. So that's context free too.
Right. If you double bar any language, you get the original back.
Right.
Yeah.
So then all you have to say is the complement of that right there.
Right.
Is not closed. And
Right. Yeah. So the complement of this is 0 to the n, 1 to the n, 2 to the n,
Right.
and we know that's not context free. Right. So we would just have to show that this is context free. The complement right here is context free.
Right. Yeah. Okay. All right.
So let's see. Well, what do the strings in here look like? So every string that is not of the form 0 to the n, 1 to the n, 2 to the n. So what has to appear? Well, note what the language looks like. It says zeros followed by ones followed by twos, and the same number of them. So what could possibly go wrong? So all strings in L are, or not are, have one of the following. Well, what string is not in any of the 0 to the n, 1 to the n, 2 to the n ones? So name a string that is not in the original language.
3.
The alphabet 0, 1, 2.
0, 2. Oh,
Yeah, 0, 2. Yeah, so that's 1.
0, 2, 0. Sorry. Because, like, if 1 was.
Mm-hmm.
Yeah. I was like, yeah.
Yeah, so that's definitely true because your original example of 0, 2, because the number of each of the 3 parts is not the same. So, but we're going to get to that. But your second example is actually closer to what I was asking. So of 2, 0. So 2, 0 can't appear in any string, right? So all strings that have 0, 2, sorry, not 0, 2, 2, 0 as a substring. What else could appear as a substring that that's not in the original language?
1, 0.
Yeah, 1, 0. Yep. What else could appear?
2, 1.
Yeah, 2, 1. I think those are the only cases for this part at least. So is there a way that I can describe all the strings that have 2, 0 in them somewhere? Yeah, how can I do it? So anything can appear, then 2, 0, then anything can appear. So what does that say to you? What does that say to you? We can make an NFA even easier.
We can make a grammar.
We can make a regular grammar.
Oh, I was gonna go. We can make a context-free grammar.
Yeah, we can make a grammar. I'm going to do one simpler, and let's just make a regex out of it. So I can say sigma star, which is just anything can appear, 2, 0, sigma star. It actually won't matter that we can make a regex out of this. What do we know about the set of all strings with 2, 0, though? Because I made a regex out of it. It's regular. That's what I wanted to say. So what we can claim is that the 2, 0 case is regular. What about the 1, 0 case? Is that the same story? Yeah, I think that's the same. And then 2, 1, yeah, that's also regular. So all strings that, yeah, go ahead, sorry.
I'm confused on how you got all strings of L have one of the following.
Yeah, so I'm defining L here to be every string not of the form 0 to the n, 1 to the n, 2 to the n. These are not all the cases. There are more after this. But if you have 2, 0 somewhere in there, you're not of the form 0 to the n, 1 to the n, 2 to the n. There are other cases, though, that we're going to handle here. Any questions on these first 3 cases? So what we have so far is a regular language, union, a regular language, union, a regular language. Because L is just the union of all these. Every string of one of these forms belongs into L. Well, what else could go wrong? So if it's not one of these first 3, then it must be zeros followed by 1s followed by 2s. But what happened? The numbers are different. Cool. So we have 0 to the I, 1 to the j, 2 to the k, where I is not equal to j. And I don't care what k is. This is just one case. There are several. So here I'm just saying that the number of zeros and ones is different. But the 2s can be any number. So clearly, this is not of the form 0 to the n, 1 to the n, 2 to the n. So how can I describe this into something that we know? Can I make a regex out of this? No, because I not equal to j, you can show that it's not regular. Can I make a grammar out of it? Yeah, how do we do it? So there are several cases. I'm only going to do one of them purely for time and sanity reasons. So let's see. Well, the 2s I don't care about. So what I'm going to do is I'm going to have the start variable go to A or B, where B is just going to produce all of the 2s. Oh, no, sorry. Not A or B. A concatenated with B. That's what I meant. Because I want the 2s at the end. So what I want the variable A here to do is to make strings of the form 0 to the I, 1 to the j, where they have different numbers of zeros and ones. So let's see. Well, if I is not equal to j, well, is it controversial to say it is either less than j or more than j? I think that's pretty fair. So I'm going to have 2 variables, one to handle there's more 1s, and the other case to have there are fewer 1s than zeros. So here, what I'm going to do is I'm going to have 2 variables, c or d. So the c variable is going to have 0 to the I, 1 to the j, where I is, let's just do less than j for that one. And the d variable is for the other case, where I is bigger than j. So more zeros than ones. Let's go through. So how would we normally make a 0 to the n, 1 to the n grammar? For the variable c here.
0C1.
Yeah, 0c1, or normally we would have epsilon, but we can't have the same number of zeros and ones. So for the c variable, this is where we have more ones than zeros. So what I'm going to do is I'm going to go to a variable e here, where e is just going to spit off ones. So the c variable is just making zeros and ones as it's going. Yeah, yeah, I can fix it with 1e or 1. Because, actually, let me make the 1 clearer. Because it's kind of looking like the or sign. Yeah, that looks a lot better. So here, the c variable is just making zeros and ones in tandem. And then the e variable is going to spit off some more ones in the middle. At least one more 1 here. And then how do we handle the d variable? We're going to do almost the same thing, 0d1, or f, where f is going to spit out zeros, because in that case we have more zeros than ones. Yeah.
For the C1, what if it never takes the E and just keeps making the same amount of zeros and ones?
Because now
Because then it'll
there's
still have to go to an end of some sort. Yeah.
right, because there's always a variable if you just stick with that rule. Yep. So we're forcing it, if it wants to make a string, to go through the E path. Pretty cool. And then the D and F variables are almost the same. So what can we claim? So the details aren't really that important here. What can we claim about the 0 to the I, 1 to the j, 2 to the k here? What can we claim that language is? It's context-free. It's a context-free language. So that's one thing that could go wrong. Another thing that could go wrong is the number of zeros and twos doesn't match. So in that case, we have 0 to the I, 1 to the j, 2 to the k, where I is not equal to k. And the third and final case is when we have same thing, but j is not equal to k. So the number of ones and twos doesn't match. If it doesn't fit into any of those camps, well, then they're all the same, but that's not the complement language that we're talking about here. At least one of the pairs must be wrong. So what can we claim about these two? Do you want me to make a grammar for them, or can we just accept on blind faith that they're context-free? I think we can accept that. So I invite you to actually make them yourself, but just to see that it really does work, but I claim that they're a context-free language too, in a very similar way to the other ones. Okay, well, let's see. Well, that's all that could possibly go wrong, because either the order of the characters is messed up, which we've handled before, or the order is right and the counts are wrong. And we handled all the possible ways the counts could go wrong. So let's see. Well, we have a regular language, union irregular, union irregular, union a context-free, union context-free, union context-free. So what is the result then after all those unions? Better taxes? No, I'm kidding. What was it?
Context.
Yeah, it's context free. So L is a context free language. But what do we know about L bar? The complement of L.
It's not.
Yeah, it's not context free. Hey, have any of you seen like a little either white square or a black square at the end of a proof? Yeah, and that's it. So what we've shown is that if you take a context-free language, its complement might not be context-free, sadly. Any questions on how that went? Yeah.
Didn't we just show like all the cases where of L that's not in a language? Are like things that aren't in the language?
Right. So.
And, like our results were regular, and context.
Right. So we're talking about the complement language here, not the original one. So we're not talking about 0 to the n, 1 to the n, 2 to the n. We're talking about the complement of 0 to the n, 1 to the n, 2 to the n.
And that's context.
And we showed that's context free. Yes. You got a question, Christian? Okay. Okay. Any other questions? Okay, so well, that's kind of sad. Not complement. You want to tick off union? Intersection here.
Yeah.
All right, let's do it. So, second result, CFLs not closed under intersection. This one's actually even easier than the previous one. So let's see. If we want to prove this, what would we have to show? If this was true, what would we have to show? Yeah.
That if we intersect two CFLs, we go outside of them.
We're not guaranteed to, but we can find examples that. Right. So, because it could be the case that it is context free, but it sometimes might not be. You want to say something? Okay. So we would want to find two languages whose intersection is a non-context free language, where the original two are context free. So we take two context free, intersect, we get a non-context free out of it. So what non-context free language do you think we should use? We just used it. 0 to the n, 1 to the n, 2 to the n. So let's let L be 0 to the n, 1 to the n, 2 to the n, our famous non-context free language. What is a very, very similar language to this one that is context free that we've shown before? Yeah. So what if we augment this language to say, I'm going to have 0 to the n, 1 to the n, but you can have any number of 2's that you want. I don't care about those. So let's see. L1, I'm going to call it to be 0 to the n, 1 to the n, 2 to the m, where n and m are at least 0. So let's see. What is the status of L1 here?
Context free.
It's context free. And what would be a way that we can show is context-free? Just by agreeing with Professor Ryan, or?
We kind of just made it.
We just make a grammar for it. So how can we make a grammar for this? Well, let's see. Does the number of 2's depend on the number of 0's and 1's? No. So we can do a similar trick to the one we did in the previous example, where we have the start variable goes to a, b. The b spits off all of the 2's. And then the a part, in the a variable, the number of 0's and 1's has to match. So I'm just going to have 0a1 or empty, because the a part is just making the 0's and the 1's together, and we know that that's context-free. So it's a pretty simple example. But we need two languages to do the intersection properly. So I need a second language here. What do you think I'm going to select as my language this time? Well, in the first one, we have 0's and 1's have to have the same number, but the 2's can be any number. What do you think the second one's going to be?
1's and 2's have the same number, 0's can be anything.
0's can be anything. Yep. So 0 to the m, 1 to the n, 2 to the n. I honestly have no idea why people pick n and m here, and that kind of reflects on myself, because they sound so similar and they look almost identical. But anyway, so what can we say about this language? So we know L1 is a CFL. What can we say about L2? Yeah, we can make a grammar in a very similar way. Go ahead. Could we flip them? Not quite, because the 1's and 2's have to match now.
Yeah, so sorry, I mean, let's switch 0 to 1, 1 to 2, and then switch.
Almost. You can almost. The problem is that the 0's have to come first. So the a variable here would have to make all of the 0's. But the sentiment is right, yes. So then the b variable is going to make the 1's in tandem with the 2's and epsilon otherwise. So because we made a grammar for it, this is a CFL. But what do we know about these two languages' intersection? So let's see. What are the strings that are in both languages? They have to have the same number of 0's and 1's and the same number of 1's and 2's. But that means that they have the same number of 0's, 1's, and 2's. So L1 intersection L2 is equal to L, which is not a CFL. Okay, any questions about that? Okay, so let's move on to something that's not very often taught, but I think is kind of an interesting thought experiment at least. So we're not going to dive too deep into this. So I hope to finish it by Wednesday so we don't go too deep. But is to think about, well, the PDA model or the CFG model, if you like, suppose that it was deterministic. Then if it were deterministic, then we can get complement out of this. And we might be able to get intersection out of it. But at least complement, because we should mark this off too. So if we could determinize the PDA model or the CFG model, then we could potentially get complement out of it. But it's currently non-deterministic. So what we're going to talk about today and Wednesday is something called a deterministic PDA. And today we're finally going to graduate from 3-letter acronyms to 4. So this is a DPDA, deterministic PDA. You may see online sometimes on YouTube videos and whatnot, some people use NPDA for non-deterministic. So that's just our usual PDA notion. DPDA means it's deterministic. So what is this? It's a PDA such that and some criterion falls. So one thing that I should tell you is, in my experience, the criterion that I'm going to present to you right now, more students have asked to clarify this, what this criterion is, than everything else in the entire class combined. Okay? So it's not really important what it is. It's just that it trips students up. So make sure to ask questions if you don't understand what this is. Such that something is true. That exactly one of the following sets is non-empty. And then what are those 4 sets? It is delta of QAX, delta of QA epsilon, delta of Q epsilon X, and delta, yeah, yeah, that's right, yeah. Q epsilon epsilon. Did I get that right? In addition, the non-empty set has exactly 1 member. Let's just make sure I got that right. Yeah, that's right. Okay. Yeah, so sometimes I trip up on this too. But so, can anyone explain in English what this means? Or I could explain it if you don't want to.
We'll try.
Okay, good.
So with the first part, having only one of the following being non-empty implies that all the other ones are empty.
Good.
So we only have one of those rules being applied, and if we only have one of those members, or one of the sets having a member inside of it, saying that we only have one transition for one rule.
Right. One transition per, yeah. So this is saying that, well, look at the 4 possibilities. That's everything that could possibly occur. Either, go ahead.
Oh, no, wait. I was just gonna add something, it's fine.
Okay, go ahead.
I was gonna, these are the push-pop rules, right?
Yes.
Okay.
So this is saying Q is a state. The second thing is what we're reading. And the third thing is what we're popping. So this is saying for each of the 4 possibilities, either you read or don't, or pop or don't, you can only do one of those 4 things. So let's just look at a scenario. So let's say that we have a state Q right here, and we have a transition AX goes to epsilon, or it doesn't matter what you push in here. And then another transition A epsilon goes to Y, can I have those two transitions? No, because that says that the transition leaving the one that we're popping to X is matching in some sense with the other one, because we're reading the same thing, and the second one is you could take the second one if there's an X on the top of the stack. So imagine that there's an X on the top of the stack right now, and we have an A to read. I can apply the first transition, the top one, because I have an X on the top of the stack. I can also apply the second one because I don't have to pop the stack off. So in a DPDA, this is not allowed. You can't have those two different possibilities. But can I have this possibility? So let's just say I have a state here. X goes to empty, and the thing that we're reading is A. Y is the thing we're popping, and let's just say we're pushing a B, for example. Can I have these two transitions? Yeah, and the reason is that I can't apply I can't apply either transition. I can only do one or the other, or maybe some other one. But I can't be allowed to choose between them, because if I have an A to read, I could apply either one. But I can't have an X and a Y on the top of the stack simultaneously. So I can only do one of the two operations, one of the two transitions here. So if an X is on the top, I can only do the first one. For the Y, I can only have the second one. Good, so this one's A-okay. Let's do one more, because this one has tripped me up before, believe it or not. So let's have epsilon goes to $, and A, Y goes to $, also. Can I have these two transitions? So this one, you have to think a little bit. The best way to view this is it in any way possible to take either one of the two transitions at the same time? And the answer is yes. If I have an A to read and a Y on the top, I can apply the bottom one, surely, but I can also do the top one. So think of it like an NFA. That would we ever have two choices to make? And in this case we do, so therefore we can't have this. So one thing that you can note here is that if you have an epsilon transition at the beginning, you can't have any other transition. Okay, so like, let's do blue, another blue. So let's just say we have Q here, and I can't have AX goes to empty and AX goes to $. I can't have these two transitions, assuming that everything else with the state's fine. I can't have this because if I have an A on the input to read and an X on the top of the stack, then I can apply either transition, which means that the non-empty set here has at least two members because I have a choice to make. So this is not allowed either. Okay, yeah?
Really quick for this example, if the bottom transition was a B, would you be able to do it, or no?
Yes, you would. Because they have, think of it like they're incompatible with each other. So like, you can't do a transition that reads an A and a transition that reads a B at the same time.
Right. Okay.
But if one was an A and one was an epsilon, it is possible from the reading standpoint. It may not be possible from the stack standpoint, but from the reading it is. Okay? Everyone understand how a DPDA basically works? So at each point, you have exactly one transition to do every single time. So we're basically out of time here. And I want you to show that, just for your own self-thought, can we have 0 to the n, 1 to the n be recognized by a DPDA? So that's just something that I want you to think about before Wednesday. Okay, so I'll see you on Wednesday.